Right, in this presentation, we're going to be having a look at the two-stroke cycle as applied to the petrol and diesel engines. Some basic concepts that we need to look at in order to understand the timing diagram. When the piston is at its uppermost position, this is the top dead center position. The crankshaft is vertically aligned and the piston is at top dead center. When the crankshaft turns to the bottom and the piston is at its lowest position, this is known as bottom dead center. The crankshaft will be vertically aligned at its lowest point, bottom dead center. The distance between the two is the piston travel, and known as the swept volume or the piston stroke. The crankshaft rotates around the main bearing and the journal circle path, the crankshaft journal circle path, where the big end bearing is connected to. The big end follows the crankshaft journal, and the movement of the crankshaft, the rotation of the crankshaft, translates into vertical movement of the piston. So as the crankshaft rotates, the piston will be moving up and down inside the cylinder. To help define the position of the crankshaft, the flywheel is usually marked with graduations, and these graduations are marked in degrees, and somewhere close to the flywheel, close to the graduations, will be a fixed pointer, and this fixed pointer is able to be used to indicate at what rotational position the crankshaft is at. So when it comes to looking at the timing of an engine, the firing order, for instance, or the valve opening and closing, or for spark ignition timing or fuel injection timing, the number 1 cylinder is usually used as the reference cylinder. So they will start with number 1 cylinder being a top dead center. Small two-stroke engines for general use, petrol engines and diesel engines, variety of applications. These can be used in like small aeroplane model engines, lawn mowers or weed whackers or tree cutting chainsaws, two-stroke engines in motorcycles, outboard engines for boats. So they have quite a variety of application. Within the design of the two-stroke, the original design had no valves, so we would call that a valveless engine for our purpose. However, to get air in and exhaust gases out, we need ports for this, and the inlet and exhaust ports can be seen in the diagram. So the inlet ports are on the lower end of the cylinder liner, and the exhaust ports are above the cylinder liner. So the picture demonstrates an engine that uses what we would call crankcase pressurization as a way of supercharging the engine. There is no suction stroke or exhaust stroke as such, so the air has to be forced into the engine. So in this particular instance, as the piston moves upwards inside the engine, the crankcase space becomes larger and creates a suction which will draw in a petrol and oil air mixture into the crankcase space. And then when the piston moves downwards, it compresses the space. The crankcase space gets smaller. So as the piston moves downwards, the air and fuel and oil mixture will be forced up through a transfer port into the actual combustion space. And at the same time that that is happening, exhaust gases will be forced out of the exhaust port. So the piston actually acts as the valve in this particular case. It's important to note that the petrol is mixed with a premix of lubricating oil because there is no lubrication oil system as such. There is another smaller type, or to get larger, another type of two-stroke engine. In this particular case, we're looking at a diesel engine with exhaust valves. So it has no exhaust ports, it only has inlet ports built into the cylinder liner, and at the top built into the cylinder head are exhaust valves and the exhaust passage, the exhaust outlet. Also, what's of interest in this diagram is the mechanical blower, the supercharger. So when the crankshaft rotates, either by means of a gear drive or a chain drive or a belt drive, the supercharger will draw in air from the atmosphere and actually pump the air into the inlet spaces, the scavenge spaces we would know it. And then when the piston moves down, the inlet ports are opened and the pressurized air can make its way into the cylinder. So to wrap it up, the upper engine is a petrol engine, spark ignition, crankcase pressurization, no valves. The lower picture is a diesel engine. It is supercharged. It is having only inlet ports and exhaust valves. So to start with the idea of a timing diagram for the basic two-stroke cycle, we look at some notes. So as previously mentioned, there may be no valves at all. The piston acts as the valves. And then in some cases, as we saw, there might only be exhaust valves, no inlet valves. So when the piston is at bottom dead center, or traveling through bottom dead center, there is very little effective piston movement. So in that particular way, the piston does not act in any way to help pump the air and the exhaust gases. So when the piston is at bottom dead center, it's momentarily standing still and there is no effect on the airflow or exhaust gas flow. So engines rely on some form of supercharging. So we looked at crankcase pressurization already. We looked at a supercharger in the previous slide. And then there's also turbocharging by means of a turbocharger. So the basic two-stroke cycle makes up of the compression stroke, where the piston moves upwards, and as it does that, the pressure and temperature inside the cylinder increases. And then that would be followed by a combustion stroke where the fuel is ignited and the burning fuel creates a huge increase in pressure and temperature, and this pressure supplies the force to push the piston downwards again. So the basic two-stroke cycle is a compression stroke and a combustion stroke. So the two-stroke cycle in a little bit more detail. For the valveless two-stroke engine, when we're looking at the inlets and exhausts being open at the same time, there is a period of overlap, and this overlap is known as scavenging. So in the construction of the engine, the inlet ports are lower down the cylinder wall, close to bottom dead center. And then the exhaust ports will be built into the cylinder some space above the inlet ports. So in order to close the ports, the piston would pass over the ports and actually close the ports. And in the case of a valveless engine, the piston is fitted with a fairly long skirt. So when the piston is in the upper position, the exhaust ports remain closed. So as the piston travels downwards, it would be pressurizing the crankcase, and then we would call that under piston charging, and then the pressurized air and fuel mixture could transfer to the combustion space via a transfer chamber. This type of engine would be a cross-flow or loop flow scavenging. Where we have an exhaust valve, this is built into the cylinder head. There is still a certain amount of overlap. The diagram doesn't really change that much. However, the construction of the engine, there's only inlet ports in the lower part of the cylinder liner, again close to bottom dead center, and then the exhaust valves are actually placed into the cylinder head itself. In this case, we don't need to keep exhaust ports closed, so the piston has got no skirt. The engine requires a mechanical blower or a turbocharger. This type of scavenging process is known as uniflow scavenging. It is a more efficient method of scavenging or replacing burnt gases in the cylinder. Loop flow or cross-flow scavenging might not be 100% effective in removing all the spent exhaust gases. So the scavenge period is the period where the inlet and exhaust overlap are both open at the same time. You can see that in the blue quadrant close to bottom dead center in the picture. So the inlet operation details. The inlet ports opening and closing, this is done by the movement of the piston. The inlet ports, as previously mentioned, are in the lower part of the cylinder wall, and these are not adjustable. They're machined holes into the liner. So as the piston travels up, it will close the inlet ports, and as the piston travels down towards bottom dead center, it will open the inlet ports. So the period that the inlet ports are actually open for is a fixed period. It's not adjustable. In the case of a turbocharged engine, because we're supplying the air for combustion under pressure, the inlet ports may be smaller, and with smaller ports you could have a similar change in the period of inlet. However, it would still be closed, fixed, so it wouldn't be able to be variable. The exhaust port operations. The exhaust ports being higher up on the cylinder wall means that as the piston travels down during the combustion stroke, the exhaust ports will open first. And then as the piston continues to travel to bottom dead center, the inlet ports will open. And then as the piston passes from bottom dead center and moving upwards again, the inlet ports will be the first to close, and then a little time after that, the exhaust ports will close. So the period of the exhaust opening is longer than the period of the inlet opening. In an engine with exhaust ports, this period is fixed. The timing is fixed and the period is fixed. The turbocharged engine, similar to the inlet ports, they might be smaller as a result of pressurizing the air into the engine and forcing exhaust gases out. They could be having an effect on the timing by being smaller, so to reduce the exhaust opening period, making a more use of compression and power strokes. So in an engine with exhaust valve operations, older engines had fixed opening and closing timings of exhaust valves. But the newer generation and then the ultra-modern engines, exhaust valves can be mechanically controlled to open and close and stay open for longer or shorter. And the modern engines, hydraulically operated exhaust valves, are controlled by electronics and a computer program. So there's an infinite adjustment there. So the exhaust period is much longer anyway than the inlet period. So exhaust valves are positioned in the cylinder head, as mentioned before. The valves may be adjustable during running, either mechanically or hydraulically. The piston will require no skirt as there's no exhaust ports to keep closed. The engine will require supercharging or turbocharging. So for variable exhaust valve timing, the exhaust valves are actuated by rocker arms with adjustable timing positions built in, or they may be hydraulically operated with actuators, and then this hydraulic system and actuator system is electronically controlled. The petrol two-stroke engine. So during the compression stroke, starting at bottom dead center, the inlet and exhaust ports are open and a fresh charge of fuel, lubricating oil and air is being charged into the cylinder, and at the same time the exhaust gases are being forced out the exhaust ports. So this would be due to the previously discussed crankcase pressurization, where the fresh fuel and air charge passes up through the transfer passage into the combustion space. Then as the piston starts to move upwards, it will close both of these ports and the compression will take place. Otto engine, spark ignition engine, low compression engine. A point to note that during the upward stroke of the piston, underneath the piston is a low pressure, which will draw a mixture of the air and fuel and lube oil into the crankcase. This is for the next combustion to take place. So by means of a carburetor passing through some reed valves, non-return valves, the new air-fuel mixture will fill the crankcase as the piston moves upwards on compression stroke. It's important that you do not confuse this with actual inlet to the combustion space above the piston. So once we have our compressed mixture, we then need to ignite it. We add a spark. High voltage electricity is passed over the points on the spark plug, and sparks will ignite the air-fuel mixture. As the piston passes over top dead center, the consequent combustion will increase the pressure and temperature dramatically and force the piston down. As the piston moves down on its combustion stroke, it will uncover the exhaust port first, where the remainder of combustion pressure will pass out the exhaust passage, and then as the piston moves further down, the transfer port will be opened, where it allows the fresh charge of air and fuel to be pushed into the cylinder combustion space, forcing out more exhaust gases. The diesel two-stroke engine. The diesel two-stroke engine can be as small as a little engine that fits in your hand and can be used to fly a remote control aeroplane, or it can be the big 14-cylinder behemoth that powers a large cargo vessel. So diesel two-strokes are used in a variety of engines. The process or the cycle as discussed is still the same. The only difference here is that during the inlet period, only fresh air is being drawn into the engine. Okay, there is no air-fuel mixture going into a diesel engine. It's just pure air from the atmosphere. So starting at bottom dead center, the inlet and the exhaust ports are open at the same time. This is the scavenging period previously mentioned. A fresh charge of air is being forced into the cylinder either by a supercharger or by a turbocharger. At the same time, the exhaust gases are being forced out of the engine through the exhaust ports. So this would be the loop scavenging or the cross-flow scavenging taking place. Then as the piston starts to move upwards, it will close the inlet ports first, and then a little bit further on it will close the exhaust ports and compression will commence. Compressed air with high temperature and high pressure is what we would be left with at the top of the compression stroke. So being a diesel engine following the diesel cycle, it's a high compression engine, and therefore we rely on heat of compression as the ignition source. The diesel two-stroke engine, once the compressed air and the piston have reached nearly top dead center, it's time to add the fuel. The fuel injector is used to inject the fuel or atomize the fuel into the hot compressed air. The sole job of the injector is to create very small droplets sprayed into the combustion space. This allows for the droplets of fuel to mix very well with the molecules of air inside the cylinder. So good air-fuel mixing and add some heat to it, and we end up with combustion. As the fuel ignites and burns, the pressure is created and forces the piston downwards. As the piston travels down on combustion stroke, the piston will reach the point where it opens the exhaust ports first, and the remainder of the combustion pressure will pass out the exhaust ports into the exhaust passage. Then as the piston travels down further, the inlet ports will be opened, and scavenge pressure from the turbochargers or superchargers will blow into the cylinder and force the rest of the exhaust gases out. And there we've completed the two-stroke cycle. The benefit of a two-stroke engine is that every single revolution of this crankshaft produces a power stroke per cylinder. So, in summary of this presentation, we've looked at the two-stroke engine, the different types of two-stroke engines. We looked at the two-stroke cycle timing diagram, which consists of a compression stroke and a power stroke. In a little bit more detail, we looked at the valveless engine, where there's only ports, inlet ports and exhaust ports. And then we looked at the more modern versions of these engines, where there's inlet ports and exhaust valves. Where these ports or valves are open at the same time, we have a scavenging period. Crankcase pressure, mechanical blower or a turbo blower is used to force the fresh air or fuel air mixture into the cylinder when the inlet ports are opened. For a petrol two-stroke, there is no lubricating oil in a sump as such. So the lubricating oil has to be mixed with the fuel in the correct ratio, and this provides lubrication for all the moving parts in the crankcase. So we talk about a premix of fuel and oil. So the lubricating oil for a two-stroke engine is different to the lubricating oil for a four-stroke engine. And then we looked at injection timing and injection period. The thing to note is that injection timing can be variable, or it can be fixed injection timing, depending on the speed of rotation of the engine. If it's a constant speed engine, then you want fixed timing. If it's a variable speed engine, then it's desirable to have variable injection timing. The period of fuel injection is related to the size of combustion and the power demand. So the more power we demand, the more fuel we need to burn, the longer the injector injects fuel. There is a limit, however. There is only so much air available with oxygen to burn fuel. So there is a maximum amount of fuel that can be burned in a certain combustion. Right, that summarizes the two-stroke cycle for this lecture.